Example 7. We're taking the derivative, and it looks like this derivative of this function has two terms to it, two really large terms. And let me first, I want to be able to see all the exponents. Let's write it as y equals 5 minus 2x to the negative 3 plus 1/8 times, and see right here, this is the whole thing I'm doing. I'm going to write it as 2x to the negative 1 plus 1 all to the 4th. Okay, so now let's go about finding the derivative. So y prime, we're going to knock the 3 down, negative 3 down front, keep the base the way it is, subtract 1 from the exponent, and now, excuse me, multiply by the derivative of the base, which is just negative 2. Okay, let's go on to the next part. Let's pull off the 1/8. And by doing that, then all we have to really focus on is the 2x is pretty much the parentheses raised to the power. So pull the power down front, write the parentheses, the base, subtract 1 from that exponent, so now it's 3, and now multiply by the derivative of the base, which is going to be negative 2x to the negative 2. Alright, so technically now I've done all the derivative parts. All we have to do from here is clean this up. So we have y prime equal to, looks like 6, 5 minus 2x to the negative 4. Let's see, 8 times 4 is 2. 1/8 of times 4 is 2, and 2 times negative 2 would be a negative 4. Kind of bringing this more to the front, if y'all were wondering what I'm doing there. And then times 2x to the negative 1 plus 1 cubed. Okay, and then just to finish this up, there's no way that I'm going to have common bases to be able to add or work any terms together. So if we want to, the last part I was thinking of is just writing this all with positive exponents. So this would be 6 over 5 minus 2x to the 4th. Okay, minus, see, the 4 will go on top, the x squared will go on bottom. And then inside of here, since this has a positive exponent, it's going to go to the top. It'll be 2 over x plus 1 cubed. That was kind of a little interesting. So y'all go back, take 2 seconds, and look how I did all of those negative exponents. They're each in their own product. And then, so negative exponents went down to the bottoms of fractions, and positive exponents stayed up in the top. And that right there is the final answer. All right, example 8. We have the quotient rule here now. So we're going to be doing, looks like, the product rule inside the quotient rule. Or I'm sorry, the chain rule inside the quotient rule. Okay, so g prime of x, it's going to be the bottom times the derivative of the top. Okay, so the derivative of the top would be the derivative of tangent. And the derivative of tangent is secant squared. And then you keep your x as is, so 3x, and then times the derivative of your angle, which is 3. Okay, so we go through that again just one more time real quick. So it's just the bottom as is, but the derivative of the top, you take the derivative of tangent, and the derivative of tangent is secant squared. Don't mess with your angle, because then you're going to be multiplying by the derivative of your angle. Okay, so bottom times the derivative of the top minus the top times the derivative of the bottom. And then here we're going to bring down that exponent 4, leave the base the way it is, just don't change it. Subtract 1 and then multiply times the derivative of your base, which is just 1. Okay, all over the base squared. So it's an x plus 7 to the 4th, all of that squared. Okay, so running through that just one more time, because this can get a little tricky. It's the bottom as is, and then times the derivative of the top. So anytime you have an angle in there, first of all, just take the derivative of tangent. So tangent is secant squared, and keep the angle as is. So if that was, tangent of theta, then the derivative is just secant squared theta. So we don't change anything with theta, because at the very end, then we multiply by the derivative of the angle, and that kind of takes care of that part. Okay, and then minus the top as is times the derivative of the bottom. And again, when you do this, just treat it almost like if I told you to take the derivative of x to the 4th. Well, you bring the 4 down front, you subtract 1 from the exponent, and then all we do, since the base is more than just x, is you multiply by the derivative of the base. Okay, so cleaning this up, g prime is going to be x plus 7 to the fourth. And I like to put, if there's a whole number multiplied to a trig function, I like to put it in the front. So 3 secant squared 3x. Again here, let's bring this back almost to the front. I'm going to say minus 4 times x plus 7 cubed times tangent of 3x all over, looks like x plus 7 to the 8th. And to finish this up, kind of looking closely to the problem, I realized the two terms in the top and the denominator, they all have at least this whole x plus 7, they all have that in common, and the one term that they actually have in common is a cube form. So if I take away the x plus 7 cubed here, I take 3 of them from here, that's going to knock it down to 1, and I take 3 there, we'll knock it to 5. And since that's the only thing they have in common, that looks like that's pretty much what we're going to leave our answer with. So it's going to be x plus 7. See if I have enough room here. I probably don't. Maybe I shouldn't even try. Let me go down below just real quick. Wishful thinking on that one. So g prime of x is going to be x plus 7, so it's to the first power, times 3 secant squared 3x minus 4 tangent of 3x, and then all of that divided by x plus 7 to the 5th. Okay, and there's our final answer for that one. I guess if you guys wanted to, you can multiply 3 secant squared 3x to the x and the 7, but since nothing's going to combine with that tangent, then you don't have to worry about it. Example 9. And just kind of looking at our function here, we have r equals the secant of the square root of theta times the tangent of 1 over theta. Okay, so before I get started, I'm kind of wanting to rewrite that a little bit. So let's write it as secant of, and I'm going to write my angle as theta to the 1/2. So instead of square root, I'll write it as a 1/2 power, and then times tangent, and then here, instead of my angle being 1 over theta, let's write it as theta to the negative 1. So that way I really see the true exponents. Okay, so r prime is going to be the first, so this is all in a product. Here's your first and here's your second. So it's going to be the first times the derivative of the second, so I'll put that in parentheses. Derivative of the second, first of all, is what's the derivative of tangent, which is secant squared, keep the angle the way it is, then times the derivative of the angle, which is negative theta to the negative 2. Okay, so that's first times the derivative of the second, plus the second times the derivative of the first. So what's the derivative of secant? Well, it's secant of your angle, tangent of your angle, and then now all of that times the derivative of our angle, which would be 1/2 theta to the negative 1/2. Woo, this one was long. Okay, let's take 2 seconds, let's go back. So here's the first as is, times the derivative of the second, and the derivative of tangent, take the derivative of your trig function, which is just secant squared, the angle by itself, and then times the derivative of that angle. Okay, and then plus the second times the derivative of the first. So taking the derivative of the first is secant theta, your secant angle, tangent angle, and then times the derivative of your angle. All right, let's see what we can do as far as cleaning up. I'm kind of looking closely at this because all the angles, even though we have multiple secant functions in here, because all the angles are different, we really can't combine together. And the same thing on the right with the tangent and the secant, we really can't combine together. So what I might do is just write some of these that aren't with trig functions, just bring them to the front. So negative theta to the negative 2, secant of theta to the 1/2 times secant of theta to the negative 1 plus, let's bring that 1/2 theta to the negative 1/2 to the front. Then we just have tangent theta to the negative 1, secant theta to the 1/2, and then tangent theta to the 1/2. Guys, that's pretty much all I'm going to see. So hey, the hard part was done. That's awesome. We can call that one finished. Example 10. All right, in example 10, we've got this whole wonderful base here to the power of negative 2. Okay, So dy dt, because our variable here is t. So we're going to find this. Let me just write y prime. Okay, in general, all of this is to the power of -2. So we would bring down the -2 and then have to subtract 1 from our exponent, right? So it'd be like that. Like if I told you y is equal to x to the -2, you guys would just say that y prime is -2 x to the -3. Okay? The only difference here is that base, we've got to come in now and take the derivative of this base. So let's multiply now. Instead of just multiplying by the derivative of x, we've got to multiply by the derivative of the base. Okay, the derivative of 1 is 0. And now the derivative of cotangent of anything. So the derivative of cotangent is a negative cosecant squared angle. But because my angle has a variable in it, I've got to multiply by the derivative of that angle, which is going to be 1/2. Okay, so drop my power down front, subtract 1 from the exponent, and then the rest of this is taking the derivative of that base. The derivative of cotangent being negative cosecant squared times the angle, and because that angle has a variable in it, then times the derivative of that angle. Alright, so cleaning of this up, y prime is going to be -2 times 1 plus cotangent of t over 2 to the -3 times a negative cosecant squared t over 2, then times 1/2. Okay, if I want to bring this 1/2, this is all multiplied together. So if I want to, hold on, I got an extra parenthesis in there. There we go. If I want to bring the 1/2 out front with the minus, that's going to make everything out front just a +1. And that'll leave me with 1 plus cotangent of t over 2, all of that to the -3. And then back here, it's just cosecant squared of t over 2. And it looks like that. We're going to call that one finished. So there's the answer for number 10.